So after that, so the output here should be, the dimensions of the output should be the same as the input, nothing changes. Now we should apply pointwise convolution. So the pointwise convolution has the following kernel. So it's 1 by dt in the number of kernels should be d prime. So the number of kernels in pointwise convolution controls the dimensionality of the output, or the number of channels in the output. Now, since the number of channels in the output we want should be small, then what this pointwise convolution does is basically a compression. So it basically compresses the activation. So the activation has a lot of channels, dt channels, then this number of channels should be compressed, should become small, right? So after the pointwise convolution, we apply batch normalization. Now at the output of this batch normalization, the dimension of the activation is h times w times d prime. And as I told you, as I just told you, d primes should be small. That is, this activation is low dimensional, is thin. Therefore, we should not apply ReLU, because if we do, then we would cause an information loss. So this is the minor difference that I mentioned. So in the MobileNetV2, the depth-wise separable convolution applies ReLU after the depth-wise convolution and after the pointwise convolution. But in MobileNetV2, we apply the ReLU just after depth-wise convolution. We do not do that after the pointwise convolution. Otherwise, we would cause an information loss, right? So then we get our output. So d prime can take several cases. So d prime, sometimes it's equal to d, to the dimensionality of the input. Sometimes it's smaller. Sometimes it's a little bit bigger. So you should go to the table of the architecture in MobileNetV2 to see the different cases we have. So based on my exploration of this architecture, it seems that d prime has these three cases. So in the case where we have a stride that is equal to 1, and where d prime is equal to d, the output here is equal to this input. The dimensions, not the output, the dimensions of the output are equal to the dimensions of the input. So normally this should be divided by 6, because this stride is performed at this layer. Should have here is S and this is d prime. So in this case, if we have a stride of 1 and d prime equal to d, then the dimension of the output has the following dimensions: h, w, and times d. So it's the same as the input. Is the same as the input. So in this case, in this particular case, authors use a residual connection. So they take this input here and then they connect it to this thin layer, or rather they add it. So they take this output and then they add it with this input, and we get our final output. So in this case, the output should have the following dimensions: h, w times d. So this residual connection is valid only in this case. So if this is not valid, then this residual connection is removed. For instance, if this stride is not equal to 1, if this stride is equal to 2, then the spatial dimensions would be reduced by a factor of 2, so there is no point in adding the input with the output because they have different dimensions. And the same thing is true if d prime is smaller than d, or d prime is higher than d. So these activations would be compatible to be added. So therefore, the residual connection is removed in such cases. So now I'll talk about why this layer module is called the inverted residual with a linear bottleneck. So first of all, why it's called inverted residuals? Why not just residuals? Well, the reason why it's called inverted residuals is because in previous architectures, such as ResNet, they used the residual connection to connect thick layers instead of thin layers. So they had activations that are thick, like that, then some thin activations, then a thick activation again. So they used a residual connection between these thick activations. But in this case, what they did is that they inverted that. So instead of doing that, the architecture looks like this. So they have thin activations, then thick activations, like that. Then again, a thin activation. And the residual connection is between these thin activations. So it's kind of reversed, inversed. So this is why they call it inverted residual. And the residual term is, of course, because they have used the residual connection. And the motivation for using such connection is the same as in the original paper, is to help the gradients to propagate across the network. There is another two terms. There is a linear bottleneck. So bottleneck in this case, in this context, means the thin inputs and outputs. So since these inputs and outputs are thin, that is, they have a small number of channels, they call it bottleneck. But here in this bottleneck, the output here we do not apply a non-linear function on the output, which is thin. We do not apply a non-linear activation on the bottleneck layer here. So when we do not apply such non-linearity, we call it a linear bottleneck. So this is why they call it linear bottleneck. So I hope this was this clear. Now we'll talk about something else,